Fluid mechanics, the study of fluids. Kayakers know that if your weight exceeds the upward buoyant force that causes them to float, they are sunk, literally. For an object such as a kayak that is immersed in a fluid, buoyant force equals the weight of the fluid that the object displaces. Buoyant force causes a kayak to pop to the surface after a plunge down a waterfall. Very exciting, but not for me. This kayaker is hurtling over Rainbow Falls on the South Fork of the Tuolumne River in Northern California. The Tuolumne is a favorite river among advanced kayakers and rafters, prized for its exciting rapids and waterfalls. Chapter 8 Overview. 3 sections. Fluids and buoyant force defines ideal fluids, calculates buoyant force, and explains why objects float or sink. Fluid pressure calculates pressures transferred by a fluid in a hydraulic lift and explains how hydrostatic pressure varies with depth. Fluids in motion introduces the equation of continuity and applies Bernoulli's equation to solve problems of fluids in motion. Forces can cause changes in an object's motion or in its shape. Energy can be kinetic energy or potential energy. In the absence of friction, the total mechanical energy of a system is constant. The total mass of a closed system is constant. Operational understanding of the concepts of area and volume. Ask students to compare the volume of containers of different shapes with approximately the same capacity. Ability to relate density, mass, and volume in a meaningful way. Ask students to calculate mass given density and volume using correct units. Chapter Preview. The first section, Fluids and Buoyant Force, is broken down into 2 subsections, Defining a Fluid and Density and Buoyant Force. Section 2, Fluid Pressure, is entirely about pressure. Fluids in Motion, 2 subsections, Fluid Flow and Principles of Fluid Flow. What to expect. In this chapter, you will learn about buoyant force, fluid pressure, and the basic equations that govern the behavior of fluids. This chapter will also introduce moving fluids and the continuity equation. Many kinds of hydraulic devices, such as the brakes in a car and the lifts that move heavy equipment, make use of the properties of fluids. An understanding of the properties of fluids is needed to design such devices. Section 1, Fluids and Buoyant Force. 4 objectives. First is define a fluid. Next, distinguish a gas from a fluid. Next, determine the magnitude of the buoyant force exerted on a floating object or a submerged object. And last, explain why some objects float and some objects sink. Figure 1, both A, liquids, and B, gases are considered fluids because they can flow and change shape. Matter is normally classified as being in one of 3 states: solid, liquid, or gaseous. Up to this point, this book's discussion of motion and the causes of motion has dealt primarily with the behavior of solid objects. This chapter concerns the mechanics of liquids and gases. Figure 1A is a photograph of a liquid. Figure 1B shows an example of a gas. Pause for a moment and see if you can identify a common trait between them. One property that they have in common is the ability to flow and to alter their shape in the process. Materials that exhibit these properties are called fluids. Fluid, a non-solid state of matter in which the atoms or molecules are free to move past each other, as in a gas or a liquid. Solid objects are not considered to be fluids because they cannot flow and therefore have a definite shape. Liquids have a definite volume, gases do not. Even though both gases and liquids are fluids, there is a difference between them. One has a definite volume and the other does not. Liquids, like solids, have a definite volume, but unlike solids, they do not have a definite shape. Imagine filling the tank of a lawnmower with gasoline. The gasoline, a liquid, changes its shape from that of its original container to that of the tank. If there is a gallon of gasoline in the container before you pour, there will be a gallon in the tank after you pour. Gases, on the other hand, have neither a definite volume nor a definite shape. When a gas is poured from the smaller container into the larger one, the gas not only changes its volume to fit the new container, but also spreads out and changes its volume within the container. Have you ever felt confined in a crowded elevator? I absolutely have. You probably felt that way because there were too many people in the elevator for the amount of space available. In other words, the density of the people was too high. In general, density is a measure of a quantity in a given space. The quantity can be anything from people or trees to mass or energy. Mass density is mass per unit volume of a substance. When the word density is used to describe a fluid, what is really being measured is the fluid's mass density. Mass density, the concentration of matter of an object measured as the mass per unit volume of a substance. This is Table 1, densities of some common substances. Notice that hydrogen is the least dense, and that carbon dioxide is more dense than air. It will sink. Notice also the density of ice. It's less dense than water. Look at iron and mercury as well. Mercury is very dense, and gold is not the most dense. Look at osmium, much more dense than gold. Mass density is the mass per unit volume of a substance. It is often represented by the Greek letter rho. Mass density, rho, equals m over v. Mass density, mass over volume. The SI unit of mass density is kilograms per cubic meter. In this book, we will follow the convention of using the word density to refer to mass density. Table 1 lists the densities of some fluids and a few important solids. Solids and liquids tend to be almost incompressible, meaning that their densities change very little with changes in pressure. Thus, the densities listed in Table 1 for solids and liquids are approximately independent of pressure. Gases, on the other hand, are compressible and can have densities over a wide range of values. Thus, there is not a standard density for a gas, as there is for solids and liquids. The densities listed for gases in Table 1 are the values of the densities at a stated temperature and pressure. For deviations of temperature and pressure from these values, the densities of the gases will vary significantly. Buoyant force can keep objects afloat. Have you ever wondered why things feel lighter underwater than they do in the air? The reason is that a fluid exerts an upward force on objects that are partially or completely submerged in it. This upward force is called the buoyant force. The buoyant force, the upward force exerted by a liquid on an object immersed in or floating on the liquid. If you have ever rested on an air mattress in a swimming pool, you have experienced the buoyant force. The buoyant force kept you and the mattress afloat. Because the buoyant force acts in a direction opposite the force of gravity, the net force acting on an object submerged in a liquid, such as water, is smaller than the object's weight. Thus, the object appears to weigh less in water than it does in air. The weight of an object immersed in a fluid is the object's apparent weight. In the case of a heavy object, such as a brick, its apparent weight is less in the water than its actual weight is in air. But it may still sink in water because the buoyant force is not enough to keep it afloat. The language of physics. Students may need help interpreting all the symbols in the equations and relating them to prior knowledge. It may be helpful to remind students that g is free fall acceleration with a value of 9.81 meters per second squared, which allows them to find an object's weight in newtons when its mass is known in kilograms. Figure 2, A, a brick is being lowered into a container of water. B, the brick displaces water, causing the water to flow into a smaller container. C, when the brick is completely submerged, the volume of the displaced water, D, is equal to the volume of the brick. Archimedes' principle described the magnitude of a buoyant force. Imagine that you submerge a brick in a container of water as shown in Figure 2. A spout on the side of the container at the water's surface allows water to flow out of the container. As the brick sinks, the water level rises and water flows through the spout into a smaller container. Did you know Archimedes was a Greek mathematician who was born in Syracuse, a city on the island of Syracuse? According to legend, the king of Syracuse suspected that a certain golden crown was not pure gold. While bathing, Archimedes figured out how to test the crown's authenticity when he discovered the buoyancy principle. He is reported to have then exclaimed, "Eureka!" meaning "I found it." Students may wonder why the buoyant force, Fb, is treated like weight, mg, even though it pushes upward. By carefully reading the statement of Archimedes' principle, they may realize that the magnitude of that force equal the weight of the fluid that would otherwise occupy the space taken up by the submerged object. The total volume of water that collects in the small container is the displaced volume of water from the large container. The displaced volume of water is equal to the volume of the portion of the brick that is underwater. The magnitude of the buoyant force acting on the brick at any given time can be calculated by using a rule known as Archimedes' principle. This principle can be stated as follows. Any object completely or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid displaced by the object. Everyone has experienced Archimedes' principle. For example, recall that it is relatively easy to lift someone if you are both standing in a swimming pool, even if lifting that same person on dry land would be difficult. Using mf to represent the mass of the displaced fluid, Archimedes' principle can be written symbolically as follows. Buoyant force is Fb equals Fg, the weight, displaced fluid, equals mfg, magnitude of buoyant force equals weight of fluid displaced. Whether an object will float or sink depends on the net force acting on it. This net force is the object's apparent weight and can be calculated as follows. F net equals FB minus FG. Now we can apply Archimedes' principle using m naught to represent the mass of the submerged object. F net equals mfg minus m naught g. Remember that m is rho v, so the expression can be rewritten as follows. F net equals the difference between the products rho FVF minus rho naught V naught all times G. Note that in this expression the fluid quantities refer to the displaced fluid. The raft and cargo are floating because their weight and the buoyant force are balanced, so it floats. It's figure 3. When FB and FG are the same, when they're equal, they float. For a floating object, the buoyant force equals the object's weight. Imagine a cargo-filled raft floating on a lake. There are two forces acting on the raft and its cargo: the downward force of gravity and the upward buoyant force of the water. Because the raft is floating in the water, the raft is in equilibrium and the two forces are balanced, as shown in figure 3. For floating objects, the buoyant force and the weight of the object are equal in magnitude. Buoyant force on floating objects. Buoyant force equals Fg object equals m naught g. Buoyant force equals weight of floating object. Here you can see when the weight is greater than the buoyant force, the object, wherever it is, will sink in the fluid. The raft and cargo sink because their densities is greater than the density of the water. Notice that Archimedes' principle is not required to find the buoyant force on a floating object if the weight of the object is known. The apparent weight of a submerged object depends on density. Imagine that a hole is accidentally punched in the raft as shown in figure 3, and that the raft begins to sink. The cargo and raft eventually sink below the water's surface, as shown in figure 4. The net force on the raft and the cargo is the vector sum of the buoyant force and the weight of the raft and cargo. As the volume of the raft decreases, the volume of the water displaced by the raft and cargo also decreases, as does the magnitude of the buoyant force. This can be written by using the expression for the net force. F net equals the quantity rho F VF minus rho naught V naught, that quantity times G. Because the raft and cargo are completely submerged, VF and V naught are equal. F net equals the quantity rho F minus rho naught times Vg. Notice that both the direction and the magnitude of the net force depend on the difference between the density of the object and the density of the fluid in which it is immersed. If the object's density is greater than the fluid's density, the net force is negative downward and the object sinks. If the object's density is less than the fluid density, the net force is positive upward and the object rises to the surface and floats. If the densities are the same, the object hangs suspended underwater, a simple relationship between the weight of a submerged object and the buoyant force on the object can be found by considering their ratio as follows. I'm listing that there. You can please study it carefully. This last expression is often used in solving buoyancy problems. A bargain hunter purchases a gold crown at a flea market. After she gets home, she hangs the crown from a scale and finds its weight to be 7.84 newtons. She then weighs the crown while it is submerged in water, and the scale reads 6.86 newtons. Is the crown made of pure gold? Explain. Well, here's what's given. Here's a picture of the crown, and we need to know the unknown. The unknown is rho naught. So let's determine rho naught. So the use of a diagram can help clarify a problem and the variables involved. In this diagram, Ft1 equals the actual weight of the crown, and Ft2 is the apparent weight of the crown when immersed in water. Study this very carefully. This will help explain the answer. Choose an equation or situation. Again, we're going to go through this. Because the object is completely submerged, consider the ratio of the weight to the buoyant force. The weight to the buoyant force. Okay, here is the weight minus the buoyant force is the apparent weight of the object while it's immersed. Okay, rearrange, and you have negative FB, and then factor through, and you have FB, and then you have the ratios, solve for rho naught, and then you have the FB equals FG minus apparent weight. Then you're going to plug in to find the buoyant force, and the buoyant force is 0.98 newtons. Remember, we're trying to find the density of the object. Here is another shot at the givens for the data to solve the problem. Now here's another shot of the ratio of Fg over Fb, which equals rho naught over rho f. And you're going to solve for rho naught, the density of the object. So now we're going to plug in to that equation and solve for rho naught, the density of the crown. So there is the plug-in, and then calculate it, and you get 8 times 10 to the third kilograms per cubic meter. From table 1, the density of gold is 19.3 times 10 to the third kilogram per cubic meter. Because 8 times 10 to the third kilogram per cubic meter is less than 19.3 times 10 to the third kilogram per cubic meter, the crown cannot be pure gold. A piece of metal weighs 50 newtons in air, 36 newtons in water, and 41 newtons in an unknown liquid. Find the densities of the following. A, the metal. So what do we know? We know the weight of the piece of metal. We could figure out the buoyant force of the metal. There's the data, that's the givens, and the buoyant force is going to be 14 newtons. Here's the density of the metal over water, Fg over Fb. Rearrange for the density of the metal, plug in the values, and solve. There are the values. The density of the water is unknown, and it's going to be 3.57 times 10 to the third kilograms per meter cubed. Now continue. The apparent weight is AW. Again, now we can figure out the density of the liquid, and it's going to be 640 kilograms per cubic meter. A 2.5 kilogram rectangular air mattress is 2 meters long, 0.5 meters wide, and 0.1 meter thick. What mass can it support in water before sinking? Well, the first thing you understand, we're going to have to find the volume of the air that's going to fit in the air mattress. So that's the length, width, and height. So let's look at the equations, and we'll rearrange and expand some equations as needed based on the data that's given. There's the expansion of the volume, and that's what's given. And then I'm going to solve for what I need and plug in. And the answer is M equals that value. I'll subtract the 2.8 and I get 97 kilograms. A ferry boat is 4 meters wide and 6 meters long. When a truck pulls onto it, the boat sinks 4 centimeters in the water. What is the weight of the boat? So it's going to sink 0.04 meters. What volume of water is that going to represent? And then what's the weight of that volume of water? So here's the answer. The answer is going to be FG. I put down FG equals FB, expanded, plugged in, and my answer is 9.4 times 10 to the third newtons. Here is table 1. I'll need this table to solve some of the problems. An empty rubber balloon has a mass of 0.0120 kilograms. The balloon is filled with helium at 0 degrees Celsius, 1 atmosphere of pressure, and a density of 0.179 kilograms per meter cubed. The filled balloon has a radius of 0.500 meters. What is the magnitude of the buoyant force acting on the balloon? Hint: see table 1 for the densities of air. There is what's given. There's my equation. I'll expand a little bit on the equation, combine it, and now I will plug in and solve. I just brought it forward. I'll plug in my values, and I have 6.63 newtons. What is the magnitude of the net force acting on the balloon? So I need to write down what I'm given, and that's what I'm given. I'm bringing that forward, actually. Mass of helium equals the density of helium times the volume. I'll expand on the volume, bring that forward, plug in, and I can calculate the mass of the helium, which is going to be 0.0937 kilograms. Now, I put that in my givens, and now I want to solve for the net force acting on the balloon. There's the weight. I plugged in for the weight. And now I know that the buoyant force minus the weight is going to be my net force. And I plug in and I calculate 5.59 newtons. What is the difference between a solid and a fluid? What is the difference between a gas and a liquid? A solid has definite shape, while a fluid does not. A liquid has a definite volume, while a gas does not. Which of the following objects will float in a tub of mercury? So you're going to need table 1, a solid gold bead, an ice cube, an iron bolt, and 5 milliliters of water. Well, this gold will not, because it has a greater density, but all the others will float in the mercury. Mercury has a high density, but not higher than gold. A 650 kilogram weather balloon is designed to lift a 4,600 kilogram package. What volume should the balloon have after being inflated with helium at 0 degrees Celsius and 1 atmosphere pressure to lift the total load? Hint, use the density values in table 1. So that's what's given, and that's my equation. And I'm going to expand a little bit on the equation, and then solve for the mass of helium. I know that FB equals FG. You can see these problems are beginning to run together. Now remember, I need to solve for the volume. So I'm going to be rearranging this equation to solve for the volume. So I'm going to have to get my volumes on the same side of the equation. So now I can solve for V, divide through by the densities, and I have the expression that I will plug in. There's the plug-in, and bring the plug-in forward and calculate, slowly calculate, and it's 4,700 cubic meters is the volume. A submerged submarine alters its buoyancy so that it initially accelerate upward at 0.325 meters per second squared. What is the submarine's average density at this time? That hint will play a role in the problem. Study it carefully. That's what's given. And use Newton's second law. And that's the equation. I'll plug into the equation and solve for the average density. What is the submarine's average density? And that's going to be the S, the sub S. So solve through, plug in, and I get 992 kilograms per cubic meter. Many kayaks are made of plastics and other composite materials that are denser than water. How are such kayaks able to float in water? The kayak's effective density includes the material of and the air within the kayak and is less than that of water's density. Section 2, fluid pressure. Calculate the pressure exerted by a fluid and calculate how pressure varies with the depth in a fluid. Figure 5, atmospheric diving suits allow divers to withstand the pressures exerted by the fluid in the ocean at depths of 610 meters. Deep sea explorers wear atmospheric diving suits like the one shown in Figure 5 to resist the forces exerted by water in the depths of the ocean. You experience the effects of similar forces on your ears when you dive to the bottom of a swimming pool or drive up a mountain or ride in an airplane. Pressure is force per unit area. In the examples above, the fluid exerts pressure on your eardrum. Pressure, the magnitude of the force on a surface per unit area. Pressure is a measure of how much force is applied over a given area. It can be written as follows. Pressure equals force over area. The SI unit of pressure is the Pascal, which is equal to 1 Newton per square meter. The Pascal is a small unit of pressure. The pressure of the atmosphere at sea level is about 1.01 times 10 to the 5th pascals. This amount of air pressure under normal conditions is the basis for another unit, the atmosphere. For the purpose of calculating pressure, 10 to the 5th pascals is about the same as 1 atmosphere. The absolute air pressure inside a typical automobile tire is about 3 times 10 to the 5th pascals, or 3 atmospheres. Applied pressure is transmitted equally throughout a fluid. When you pump a bicycle tire, you apply a force on the pump that in turn exerts a force on the air inside the tire. Students may confuse the air increase in Pascal's principle with the pressure of the fluid inside. While an increase in pressure is transmitted equally throughout a fluid, the total pressure at different points in the fluid may vary. For example, with depth, the air responds by pushing not only against the pump, but also against the walls of the tire. As a result, the pressure increases by an equal amount throughout the tire. In general, if the pressure in a fluid is increased at any point in a container, such as at the valve of the tire, the pressure increases at all points inside the container by exactly the same amount. Blaise Pascal, 1623 to 1662, noticed this fact in what is now called Pascal's principle or Pascal's law. Pascal's principle: pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and to the walls of the container. Figure 6. The pressure is the same on both sides of the enclosed fluid, allowing a small force to lift a heavy object. Please study this illustration very carefully. A hydraulic lift, such as the one shown in Figure 6, makes use of Pascal's principle. A small force applied to a small piston of area A1 causes a pressure increase in a fluid such as oil. According to Pascal's principle, this increase in pressure is transmitted to a larger piston of area A2, and the fluid exerts a force, F2, on the piston. Applying Pascal's principle and the definition of pressure gives the following equation below. Please study it very carefully. Rearranging this equation to solve for F2 produces the following. F2 equals the ratio A2 over A1 times the quantity F1. This second equation shows that the output force F2 is larger than the input force F1 by a factor equal to the ratio of the areas of the two pistons. However, the input force must be applied over a longer distance. The work required to lift the truck is not reduced by the use of a hydraulic lift, just like a simple machine. The small piston of a hydraulic lift has an area of 0.2 square meters. A car weighing 1.20 times 10 to the fourth newtons sits on a rack mounted on the large piston. The large piston has an area of 0.9 square meters. How large a force must be applied to the small piston to support the car? Here's given. I'm looking for F1. I'm going to choose the equation or situation, use the equation for pressure, and apply Pascal's principle. So I'm going to solve for F1. I'm going to plug in my values. Again, very, very simple, a proportional relationship. There are my values. There's my plug-in. I'm going to calculate the value, and I get 2.7 times 10 to the fourth newtons for F1. In a car lift, compressed air exerts a force on a piston with a radius of 5 centimeters. This pressure is transmitted to a second piston with a radius of 15 centimeters. How large a force must the compressed air exert to lift a 1.33 times 10 to the fourth Newton car? Here's what's given. Don't forget to change it to meters. Also, it's a circle, so you're going to change the areas to pi r squared, and you're going to solve for F1, and you're going to, I'm bringing the equation forward, give myself some more room. I'm going to plug in, and I'm going to calculate. And it's 1.4 times 10 to the fourth newtons. What pressure produces this force? Neglect the weight of the pistons. Well, there's my pressure equation, and I'm going to plug in. Don't forget the pi r squared, and I have 1.88 times 10 to the fifth pascals. A 1.5 meter wide by 2.5 meter long waterbed weighs 1,025 newtons. Find the pressure that the waterbed exerts on the floor. Assume that the entire lower surface of the bed makes contact with the floor. Very simple problem, force over area. There's my givens, there's my equation. Don't forget that the Fg is the force, that's the weight, width times length, and it's going to be 270 pascals. A person rides up a lift to a mountaintop, but the person's ears fail to pop. That is, the pressure of the inner ear does not equalize with the outside atmosphere. The radius of each eardrum is 0.4 centimeters. The pressure of the atmosphere drops from 1.010 times 10 to the fifth pascals at the bottom of the lift to 0.998 times 10 to the fifth pascals at the top. A. What is the pressure difference between the inner and outer ear at the top of the mountain? So the first thing I need to do for A, well, the only thing I need to do for A is I want to find the difference in the pressures. So I subtract and find my pressure net, my two pressure changes. So it's going to be 1.2 times 10 to the third pascals is going to be the difference. What is the magnitude of the net force on each eardrum? So now I have my radius, change it to meters, and I'm going to, I know that P equals F over A, so PA will equal F net, and then make sure that you understand that it's a circle, substitute in pi r squared, then plug in and solve. There are my values plugged in, and I have a calculator, and it's going to be 0.06 newtons. Pressure varies with depth in a liquid. As a submarine dives deeper in the water, the pressure of the water against the hull of the submarine increases, so the hull must be strong enough to withstand large pressures. Water pressure increases with depth because the water at a given depth must support the weight of the water above it. Imagine a small area on the hull of the submarine. The weight of the entire column of water above that area exerts a force on the area. The column of water has a volume equal to AH, where A is the cross-sectional area of the column and H is the height. Hence, the mass of this column of water is M equals rho V equals rho A H. M equals rho V equals rho A H. Using the definition of density and pressure, the pressure at this depth due to the weight of the column of water can be calculated as follows. So I'm going to finally come up with P equals rho Hg. This equation is valid only if the density is the same throughout the fluid. The pressure in the equation above is referred to as gauge pressure. It is not the total pressure at this depth because the atmosphere itself also exerts a pressure at the surface. Thus, the gauge pressure is actually the total pressure minus the atmospheric pressure. By using the symbol P naught for the atmospheric pressure at the surface, we can express the total pressure or absolute pressure at a given depth in a fluid of uniform density rho as follows. fluid pressure as a function of depth. P equals P naught plus rho GH. Pressure equals atmospheric pressure plus the product density times free fall acceleration times depth. This expression for pressure in a fluid can be used to help understand buoyant forces. Figure 7, the fluid pressure at the bottom of the box is greater than the fluid pressure at the top of the box. And everywhere in between, the arrows would be increasingly larger as you go down the sides of the box. Very important diagram. Let's do a visual strategy for figure 7. Point out that the fluid exerts force in all directions because of the pressure. Pressure against the sides of the box also increases with depth. Question 1. Suppose the box in the diagram is immersed in water and L equals 2 meters. How does pressure on the box's sides, 1 meter from its top, compare with pressure on the sides near the top and near the bottom? Delta P equals rho G delta H, which all equals 9,800 pascals. This means that the pressure on the middle area of the sides of the box is 9,800 pascals higher than the pressure near the top and 9,800 pascals lower than the pressure near the bottom of the box. Consider a rectangular box submerged in a container of water as shown in figure 7. The water pressure at the top of the box is negative the sum P naught plus rho GH1, and the water pressure at the bottom of the box is P naught plus rho GH2. From the definition of pressure, we know that the downward force on the box is negative A times the sum P naught plus rho GH1, where A is the area of the top of the box. The upward force on the box is A times the sum P naught plus rho GH2. The net force on the box is the sum of these two forces. So ultimately, F net will equal rho GV, which equals MFG. Note that this is an expression of Archimedes' principle. In general, we can say that buoyant forces arise from the differences in fluid pressure between the top and the bottom of an immersed object. Section review number 1. Which of the following exerts the most pressure while resting on the floor? A 25 Newton cube with 1.5 meter sides. There's given. And I'm going to do the pressure. And there's my equation. Solve. And I get 11 pascals. Okay. A 15 Newton cylinder with a base radius of 1 meter. Okay, very large area. So there's my givens. And don't forget the pi r squared. There's my equation. Plug in. And I get 4.8 pascals, much lower. And then I have a 25 Newton cube with a 2 meter sides. All right, 2 meter sides. All right, so a cube. So it's going to be, there's the equation. Don't forget it's going to be the side squared. So it's going to be 25 divided by 4, which is 6.2 pascals. And then the last is 25 Newton cylinder with a base radius of 1 meter. All right, so instead of a square, it's going to be a circle. Don't forget the pi r squared. We're going to plug in, and we're going to get 8 pascals. So the answer is A, is the largest pressure. A is the largest pressure. Okay. Water is to be pumped to the top of the Empire State Building, which is 366 meters high. What gauge pressure is needed in the water line at the base of the building to raise the water to this height? Make sure you look at table 1. There are the given, and P equals rho GH. I'm going to plug in, and there I have it, 3.59 times 10 to the 6 pascals. When a submarine dives to a depth of 5 times 10 to the 2 meters, how much pressure in pascals must its hull be able to withstand? How many times larger is the pressure than the pressure at the surface? Aha, as they're about to say when the plot thickens. Hint, see table 1 for the density of seawater. There's given, that's what's given, that's all my values, my data. There's my equation. Remember, I want the total pressure, so I need V naught plus rho GH. I'm going to plug in, and I have 5.1 times 10 to the 6th pascals. And now you're going to figure out what N is. We have to have the ratio. So the ratio is going to be the pressure over the P naught, and that's the ratio, that's the plug-in, and N equals 50. Calculate the depth in the ocean at which the pressure is 3 times atmospheric pressure. I can do that in my head. It's going to be about 20 meters. And I will show you in class how I did that. Very simple. So here are my givens. Don't forget P equals 3P naught. And that's my equation. And I'm going to solve for H. So I've got to plug in for P. So P is 3P naught. So that's my plugins. And 20.1 meters. Section 3, fluids in motion. Examine the motion of a fluid using the continuity equation. Recognize the effects of Bernoulli's principle on fluid motion. Have you ever gone canoeing or rafting down a river? If so, you may have noticed that part of the river flowed smoothly, allowing you to float calmly or to simply paddle along. At other places in the river, there may have been rocks or dramatic bends that created foamy whitewater rapids. When a fluid, such as river water, is in motion, the flow can be characterized in one of 2 ways. The flow is said to be laminar if every particle that passes a particular point moves along the same smooth path traveled by the particles that passed the point earlier. The smooth stretches of the river are regions of laminar flow. In contrast, the flow of a fluid becomes irregular or turbulent above a certain velocity or under conditions that can cause abrupt changes in velocity, such as where there are obstacles or sharp turns in the river. Figure 8. The water flowing around this cylinder exhibits laminar flow and turbulent flow. It's labeled appropriately. Please study the illustration carefully. Irregular motion of the fluid, called eddy currents, are characteristic of turbulent flow. Figure 8 shows a photograph of water flowing past the cylinder. Hydrogen bubbles were added to the water to make the streamlines and the eddy currents visible. Notice the dramatic difference in flow patterns between the laminar flow and the turbulent flow. Laminar flow is much easier to model because it is predictable. Turbulent flow is extremely chaotic and unpredictable. The ideal fluid model simplifies fluid flow analysis. Many features of fluid motion can be understood by considering the behavior of an ideal fluid. Ideal fluid, a fluid that has no internal friction or viscosity and is incompressible. Although no real fluid has all the properties of an ideal fluid, the ideal fluid model does help us explain many properties of real fluids, so the model is a useful tool for analysis. While discussing density and buoyancy, we assume all of the fluids used in problems were practically incompressible. A fluid is incompressible if the density of the fluid always remains constant. The term viscosity refers to the amount of internal friction within a fluid. A fluid with a high viscosity flows more slowly than does a fluid with a low viscosity. As a viscous fluid flows, part of the kinetic energy of the fluid is transformed into internal energy due to the friction of the fluid particles sliding past each other. Ideal fluids are considered non-viscous, so they lose kinetic energy due to friction as they flow. Ideal fluids are also characterized by a steady flow. In other words, the velocity, density, and pressure at each point in the fluid are constant. Ideal flow of an ideal fluid is also non-turbulent, which means that there are no eddy currents in the moving fluid. Figure 9, the mass flowing into the pipe must equal the mass flowing out of the pipe in the same time interval. Study this very carefully. This is going to become very important in the next few slides. Figure 9, point out that the volumes of the two shaded sections of the pipe must be equal in order for the continuity equation to apply. Assume A1 is smaller than pictured in figure 9. Question 1. Would delta x1 need to be longer or shorter for the mass of the liquid in each section to still be equal? It should be longer. Fluid behavior is often very complex. Several general principles describing the flow of fluids can be derived relatively easily from basic physical laws. The continuity equation results from mass conservation. Imagine that an ideal fluid flows into one end of a pipe and out the other end, as shown in figure 9. The diameter of the pipe is different at each end. How does the speed of fluid flow change as the fluid passes through the pipe? Think a hose, you're watering your garden. It's very important to consider a hose. And say the hose is two different hoses, a larger one and a smaller one. Because mass is conserved and because the fluid is incompressible, we know that the mass flowing into the bottom of the pipe, M1, must equal the mass flowing out of the top of the pipe, M2, during any given time interval, M1 equals M2. This simple equation can be expanded by recalling that M equals rho V and by using the formula for the volume of a cylinder, V equals A delta X. So you have rho 1 V1 equals rho 2 V2. Rho 1 A1 delta X1 equals rho 2 A2 delta X2. The length of the cylinder, delta X, is also the distance the fluid travels, which is equal to the speed of flow multiplied by the time interval. Delta X equals V delta T. And the equation below would be rho 1 A1 V1 delta T equals rho 2 A2 V2 delta T. The time interval and for an ideal fluid, the density are the same on each side of the equation, so they cancel each other out. The resulting equation is called the continuity equation. A1 V1 equals A2 V2. Area times speed in region 1 equals area times speed in region 2. The speed of fluid flow depends on cross-sectional area. Note in the continuity equation that A1 and A2 can represent any two different cross-sectional areas of the pipe, not just the ends. This equation implies that the fluid speed is faster where the pipe is narrow and slower where the pipe is wide. The product, AV, which has units of volume per unit time, is called the flow rate. Flow rate. It is the volume of fluid which passes per unit time, usually represented by the symbol Q, sometimes capital V. The SI units is m cubed per s, cubic meters per second. The flow rate is constant throughout the pipe. The width of a stream of water narrows as the water falls and speeds up. The continuity equation explains an effect you may have observed as water flows slowly from a faucet, as shown in Figure 10. Because the water speeds up due to gravity as it falls, the stream narrows, satisfying the continuity equation. The continuity equation also explains why a river tends to flow more rapidly in places where the river is shallow or narrows than in places where the river is deep and wide. Rivers run deep. A leaf speeds up as it passes into a constriction in a drainage pipe. The water pressure on the right is less than the water pressure on the left. Study this very carefully. It has to do with Bernoulli's principle and ultimately how planes fly. The pressure in a fluid is related to the speed of flow. Suppose there is a waterlogged leaf carried along by the water in a drainage pipe as shown in Figure 11. The continuity equation shows that the water moves faster through the narrow part of the tube than through the wider part of the tube. Therefore, as the water carries the leaf into the constriction, the leaf speeds up. If the water and the leaf are accelerating as they enter the constriction, an unbalanced force must be causing the acceleration according to Newton's second law. This unbalanced force is a result of the fact that the water pressure in front of the leaf is less than the water pressure behind the leaf. The pressure differences cause the leaf and the water around it to accelerate as it enters the narrow part of the tube. Figure 12, as air flows around an airplane wing, the air above the wing moves faster than the air below, producing lift. Please study Figure 12 carefully. It has to do with Bernoulli's principle, and it becomes very important as we proceed. This behavior illustrates a general principle known as Bernoulli's principle, which can be stated as follows. Bernoulli's principle: the pressure in a fluid decreases as the fluid's velocity increases. The lift on an airplane wing can be explained in part with Bernoulli's principle. As an airplane flies, air flows around the wings and body of the plane as shown in Figure 12. Airplane wings are designed to direct the flow of air so that the air speed above the wing is greater than the air speed below the wing. Therefore, the air pressure above the wing is less than the pressure below, and there is a net upward force on the wing called lift. The tilt of an airplane wing also adds to the lift on the plane. The front of the wing is tilted upward so that the air striking the bottom of the wing is deflected downward. Misconception. One might think that water coming out of a hose is at a higher pressure than the water in the hose, but the opposite is true. The pressure outside the hose is atmospheric pressure, while the pressure inside the hose is higher than the atmospheric pressure. In fact, the water flows out of the hose because the greater pressure in the hose results in a net force on the water at the end of the hose, which pushes the water out. Section review. Water at a pressure of 3 times 10 to the 5th pascals flows through a horizontal pipe at a speed of 1 meter per second. The pipe narrows to 1/4 its original diameter. What is the speed of the flow in the narrow section? There's P1 and V1 is 1 meter per second. And I know that R2 equals 1/4 R1. And write my equation. Now watch the derivation closely. I'm actually going to derive the equation, and it's going to be a very simple equation. Now here are all of the values I'm plugging in and then simply canceling. The R1 squareds can cancel, and I'm left with V2 equals 16 times V1. And V2 is going to equal 16 meters per second. A 2 centimeter diameter faucet tap fills a 2.5 times 10 to the negative 2 cubic meter container in 30 seconds. What is the speed at which the water leaves the faucet? Well, that's what I have. You can see that things are converted to the correct unit labels. V equals flow rate over A, and then I'm going to substitute in the flow rate for V over delta T, and then combine the equation and simplify, and then plug in. And I'm going to come up with a velocity of 2.7 meters per second. The time required to fill a glass with water from a large container with a spigot is 30 seconds. If you replace the spigot with a smaller one so that the speed of the water leaving the nozzle doubles, how long does it take to fill the glass? Aha. 30 seconds, because the volume rate of flow is constant. Aha, as they say when the plot thickens. For this problem, refer back to figure 9. Assume that the cross-sectional area, A2, in the tube is increased. Would the length, delta x2, need to be longer or shorter than the mass of the liquid in both sections to still be equal? So what equations would you need? How would you calculate this value? As they say when the plot thickens, it would simply need to be shorter. Key ideas, section 1, fluids and buoyant force. Force is a vector quantity that causes changes in motion. A fluid is a material that can flow, and thus it has no definite shape. Both gases and liquids are fluids. Buoyant force is an upward force exerted by a fluid on an object floating on or submerged in the fluid. The magnitude of a buoyant force for a submerged object is determined by Archimedes' principle and is equal to the weight of the displaced fluid. The magnitude of a buoyant force for a floating object is equal to the weight of the object because the object is in equilibrium. Section 2, fluid pressure. Pressure is a measure of how much force is exerted over a given area. According to Pascal's principle, pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and to the walls of the container. The pressure in a fluid increases with depth. Section 3, fluids in motion. Moving fluids can exhibit laminar smooth flow or turbulent flow. An ideal fluid is incompressible, non-viscous, and when undergoing ideal flow, non-turbulent. The continuity equation is derived from the fact that the amount of fluid leaving a pipe during some time interval equals the amount entering the pipe during the same time interval. According to Bernoulli's principle, swift moving fluids exert less pressure than slower moving fluids. This is your table on variable symbols. Study it carefully, quantities, units, and conversions.